Thank you for joining our first webinar in our 5-part Open-NFP Spring Webinar Series. Today, Ted Drapus and Chris Telfer, with special panelist Typhoon Goal, are going to present OpenContrail Real Speed Offloading vRouter. This webinar will discuss how Netronome has added support for transparent hardware acceleration of OpenContrail's vRouter data plane using Agilio hardware. Ted and Chris will cover the architecture of the system and how to support transparent offload in the context of a split data plane, as well as provisioning of NFP resources required to produce a performant solution. A copy of the presentation, archived replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page on the OpenNFP.org website. Ted Drapus is a director of software engineering at Netronome, leading the vRouter acceleration effort. Ted has 10 years of experience at Netronome working on security appliance and SDN software. Chris Telfer is a distinguished software engineer at Netronome, where he has worked for the past 8 years. Among other endeavors, he works on the vRouter acceleration project at Netronome. Let me describe Open-NFP before I turn it over to Ted and Chris. Open-NFP's objective is to support and grow reusable applied research and technology development in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in the space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems, and direct support from our engineers and our research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars, such as the one we are performing today. We encourage proposals to research funding agencies. We invite you to join the 40+ universities and companies working directly with Open-NFP through projects. On today's agenda, we will cover an introduction to OpenContrail and OpenContrail vRouter, NFP acceleration strategy, software, architecture, results and conclusions, and then on to questions. We would like to thank Juniper Networks for providing this slide. If you would like to learn more about what Contrail is beyond what we are going to talk about today, all of the source code is freely available, which has also allowed Netronome to engage with Contrail immediately. As a result of their work, they've also upstreamed code into OpenContrail as a part of this effort and work with Juniper Contrail engineering and test teams. Over to you, Ted.
So Contrail is built upon standards-based protocols for interop, BGP being primarily the one we're highly interested in, because that allows one to scale networks very easily using standard technology. It provides all the components necessary for network virtualization, and we've primarily focused on KVM hypervisors. It is API rich, that allows for automation and testing, and it is a carrier-grade platform for cloud infrastructure. It is commercially deployed at many telcos and data center operators across the world. So we're not talking about a project. This is a significant open source initiative. So like other networking products, we can break up OpenContrail into a control section and a data plane section. So obviously, OpenContrail controller is the name for their controller. It is a software-defined networking controller that is responsible for management, control, and analytics of the virtual network. And the piece we're primarily going to be interested in or talking about or talking to is the OpenContrail vRouter. It is a programmable of course, by the controller, data path for managing data center networks. So further detail on vRouter. Again, it is programmable by the controller, so it connects to an underlay network and manages overlay networks running on the various compute nodes in a data center. Similar to OVS, but it's specifically designed for data center scalability. It connects, it sets up point-to-point tunnels over the underlay for setting up virtual networks, and it deploys or utilizes the following tunneling protocols that are configurable by the user, by the data plane, by the controller. And they are all listed here: MPLS over UDP, MPLS over GRE, and then VXLAN is available for actually creating L2 only overlays as well. It is distributed, so it doesn't live in any central location. It lives on it's spread across and lives on all the compute nodes in the system, running in the hypervisor. It acts as an L2 switch in some cases, depending on how you want to set up your overlays, or it acts as an L3 router to connect your nodes, right? So sometimes this is often referred to as a layer 3 SDN type solution, hence the name vRouter versus vSwitch. It does have both a kernel module implementation and a DPDK user space implementation built from the same code base, right? And that code base, again, is all open sourced on OpenContrail.org. So pictorially, what are we looking at? vRouter in a compute node, and the piece in the middle is what we're really going to focus on here in terms of the data plane side of things. So vRouter KO, the kernel module data plane that I alluded to in the previous slide. The way this is drawn, on the underlay you have a standard NIC or a NIC, and Contrail supports one physical or one logical device as an interface to the underlay. Hence you see a bond of the two ports of the NIC. The data plane consists of, is running in the agent and in the vRouter kernel module. The agent is responsible for security group classification, initial flow classification, flow setup, timing outflows. So it's the smart part of the data plane. It also interfaces to the controller for management, right? So it's a dual purpose module, interfacing with control, and it's the intelligent portion of the data plane, setting up flows and doing classification. The main forwarding path is the vRouter kernel module, taking traffic from the underlay, delivering it to the overlay, and vice versa, taking traffic from the overlay, delivering traffic to the underlay. So in 30 seconds, that's essentially what's going on a compute node in a data center. But I'll say, so why the NFP, or why a smart NIC running an NFP versus a standard NIC that's sitting in the previous picture? So how did vRouter evolve over time, prior to our engagement, right? It initially started out as a kernel vRouter module, as shown in the previous picture, right? With packet delivery to the overlay via tap, and I guess tap to a vhost interface later on. But again, because you're going between kernel and user space, this tends to be slow. So along came an effort. Again, it's an open source project. There was an effort to create a user space implementation to remove that kernel to use user space interaction, right? So DPDK vRouter came along, and this did significantly improve the PPS compared to what the kernel vRouter was able to achieve. But you do have to use cores to achieve significant performance, and it can scale. But the question is, how many cores do you want to dedicate on your compute node to the forwarding plane, to DPDK vRouter? So, and I don't want to obsess with specific numbers. I just put this number out for the sake of discussion. Everybody who measures performance using a DPDK app is going to get a different number. So when one talks about performance, you have to ask yourself, we always get asked what's the performance in any project that you're doing, right? But it's always performance doing what and under what configuration. So so it's always relative, and and I want to speak in relative terms. So the DPDK vRouter, yes, it did increase performance from the kernel vRouter. Let's say it's of this order of magnitude. You could even say it's 3 million packets per second for the sake of argument that it's able to achieve. But if you have a VNF that requires a high packet per second rate, you could do the math and say, well, I need it to support 15. I need to support 20 million packets per second. I need 25 million packets per second. And you can start to see where you have to dedicate a significant portion of your compute node to solving that problem and it being able to deliver packets. So there's a price you pay if you want to scale up, right? And when you pay that price, you take away resources from the VMs as well that are trying to run on a compute node. So there's a balancing act, and this works out fine. You can, but if you really need a high packet per second rate of delivery, then you need another solution, right? So incorporating the NFP to offload the vRouter data path removes those resources from running on the compute node and moves them down onto the NFP or the smart NIC, right? And then you can recover those CPU resources. The other thing that it does for you is it allows direct delivery of packets from the underlay that are being handled by the NFP directly into the overlay network via SRIOV or directly into the VM space. So those overheads are being removed from user space, from the host itself, and you're utilizing the NFP to be able to overcome those issues that slow down packet per second performance and consume resources on the host. And that leads into how the NFP achieved this, and I'll hand over to my colleague Chris Telfer, and he will take you through that.
All right, everyone. So let's talk about how we approach this problem of trying to accelerate the Contrail data path vRouter. So there were two key goals when we set out to do this, and as Ted mentioned, the main one offhand was performance, because that was the problem we were trying to solve. But a second one, and almost equally important, was transparency. We wanted to make sure that as much as possible, the existing code base would function pretty much exactly the same way, regardless of whether or not there was any acceleration present in the system. Hopefully, the end user, when they're running their VMs, all they notice is a performance boost. Hopefully, the data center manager doesn't even notice the presence of the acceleration either, and is just able to run the data center as normal, assigning and allocating VMs without regard to having special provisioning for the accelerated NICs. So the way we approached this was, well, as Ted described, you could say that the vRouter data path had this user space component and this fast path. So we approached this by making the NFP an ultra-fast path, parallel to the vRouter fast path. But the full logic that is in that fast path is actually quite substantial, and there are a lot of configuration operations that are required in there that are just not ideally suited to offload in the NFP itself. And so we settled on, we said, well, not settled on, but we early on decided that no, it didn't make a whole lot of sense to implement 100% of that fast path in the NFP. Rather, instead, we will implement the most important parts in the NFP for packet handling and movement and so forth. But then, if there are any corner cases or edge cases that just are ill-suited for NFP implementation, then we can let those packets instead fall back to the regular vRouter fast path, in this case in the kernel, and they can handle the packets as normal without even having to realize that other packets have been offloaded from them. So I just wanted to bring up this picture again to show you again what things look like in vRouter on a compute node, so that you can have that fresh in your mind as we then describe again what our solution looks like. So again, we have the agent, we have the vRouter kernel module. We're going to, in this talk about how we did it offloading the kernel module, but we could have easily have done it using the DPDK data path. We just picked one. But this is the picture to keep in mind. And just to note how right now what you see is that vRouter kernel module is attached to several interfaces, several network interfaces in the Linux kernel. vHost interfaces that are used to deliver to the VMs, and the NetDev interface, in this case through the bond, which is used to deliver to the underlay network. Okay, so we integrated into OpenContrail at 3 specific points to insert our acceleration. First of all, we had to work with the OpenContrail community and request basically a hardware offload API be inserted into the vRouter data path. Now, we did not want this to be intrusive. In fact, and we want the data path to operate regardless of whether or not the offload API is actually turned on, whether or not there's any card plugged in or not. So we restricted, we very much restricted what that API looks like. But it basically ends up being a table of function pointers in the kernel module that get invoked when certain configuration operations occur within the vRouter data path. So, for example, when somebody adds a new route to the routing table, or someone adds an interface or removes an interface or requests some stats or things like that, or programs a new flow, when the agent programs a new flow in the flow table and says, okay, release packets that are held for that flow, as we'll talk about in greater depth in a second, those sorts of operations, when they get invoked, now the data path will also invoke our function pointer hooks and say, by the way, I want you to mirror this operation in the NFP. Or in the case of, say, a statistics request, it would say, okay, here's my statistics for this interface, but please add in any extra statistics that you've been keeping counter for that interface. Okay, so again, we kept that very, very thin and hardware neutral, absolutely hardware neutral.
That API has, as I mentioned, this is an example of code that has been upstreamed into OpenContrail. So the API has been upstream. The implementation, which Chris will get into next, is covered in our corresponding kernel module.
Yep. So that was the first integration point. The second integration point is a bit more subtle, and I want to draw your attention back to those interfaces that I mentioned before. In order for the vRouter fast path to not realize that there is hardware acceleration going on, it has to still be able to send and receive packets from interfaces. But in this case, the interfaces, the main interfaces in this system, are actually going to be present in the SmartNIC itself. So what we did was we created what we call representative interfaces in the Linux kernel, which are they're sort of fake NetDevs, and they stand in for the real interfaces that exist on the SmartNIC itself. So vRouter still sees that it's plugged into a set of physical and virtual interfaces, but when it transmits on one of these representative interfaces that represents a physical interface, instead the packet gets muxed and sent down to the NFP, and the NFP then transmits it out the physical interface. If it transmits to a virtual interface, a virtual interface's representative interface, then the packet will go to the SmartNIC, and the SmartNIC will take care of delivering that packet over the appropriate virtual interface into the virtual machine that it's destined for. And the reverse is also true. When packets come in on these representative interfaces, it appears to the vRouter kernel module like they came fresh from the wire or fresh from a VM without any modification or alteration. Okay. So that's our second integration point. And our third integration point was we had to now, with these concept of representative interfaces, modify the way that interfaces were allocated, removed, and configured from the orchestration layer perspective in order to basically do the plumbing to get these interfaces hooked into VMs and into the SmartNIC and into the vRouter kernel module. Unfortunately, that was also those changes were all part of, although they're run by OpenStack, they're run as part of a script provided by Juniper's Contrail code base, so we were able to hook into that as well. Okay. So this is what our new accelerated architecture looks like. Okay. And so most of the light blue boxes there are the parts we've added, except the flow table was always part of the Contrail code base. And I talked about most of the components in here already, but just the ones to take note of. At the bottom now we have this offloaded vRouter data path, and this we hope is going to run most of the traffic, is going to handle most of the traffic going through the system. And then above that we have our own NFP vRouter kernel module, and this is our kernel module that interfaces via the offload API and the representative interfaces with the regular vRouter data path. And I mentioned the port configuration module and that's below the OpenStack agent. You can see that up near the top. Now off to the right, below VM0, there's one more component, and this was sort of an optional component, but it was found to be of significant utility for a lot of people. And this component is called the vRDIO relay daemon. Now, let me just digress a little bit away from what we were talking about before for why we use this. Okay. As I said, the NIC is going to be the one responsible for delivering packets into the VMs. And we can do that for VMs that have our SRIOV driver within them. We can do that by just using regular PCI device assignment to assign an SRIOV interface into the VM, and that's what VM1 has in this picture. It's got a native metronome driver in it, and so we can send and receive packets directly to that VM across PCIe. But there are many VMs that might be older, don't have our particular driver, or just don't have any drivers at all except for a vRDIO driver, because they are kept very small and self-contained. And for those who aren't aware, vRDIO is a virtual device standard that is very, very commonly used in virtual environments. It's ubiquitous. So in order to be able to deliver packets to and from virtual machines that only support vRDIO, we added a proxy. And again, I named this vRDIO relay D, and its job, it's just a very small, thin DPDK app, is to basically receive and send packets from our SRIOV interfaces and proxy them and deliver them directly into the vRDIO interfaces via DPDK's vhost libraries, and vice versa. When the VM delivers packets over its vRDIO interfaces, it proxies those directly into our SRIOV interfaces. So in this way, we're actually able to achieve hardware independence in this system and not have anybody have to have our SRIOV drivers, but still deliver speed and performance for packets moving in and out of the VMs. Now that comes at a little bit of a cost in terms of host CPU usage, but it's much less than we would have with DPDK, with a full DPDK data plane. And again, it's optional, depending on the workload and the requirement. Okay, so to talk about, to show how offloading works now, we're going to talk about a day in the life of the packet, in the life of a packet. This is for the first packet of a flow arriving into the system. And this packet is arriving, we'll say, from the underlay network, and it comes into the vRouter data path, and the vRouter data path looks at it and says, okay, well, this packet pertains to a flow that I don't have in my flow table. So therefore, that has to go ultimately up to the Contrail agent for classification, because that's the vRouter architecture. So I am going to deliver this on the representative interface that corresponds to the physical interface I received this from. And so the vRouter data path delivers it across PCIe to our vRouter kernel module, which demuxes it off of that PCIe control channel onto the physical interfaces, the physical interface 0's representative interface, and it arrives at the vRouter kernel module, which just sees another packet off the physical network from its perspective. And it goes and it does its own lookups and says, oh, well, I don't see a flow entry for this packet, and I should. So I guess that means this is a new flow. So I'm going to hold on to this packet, and then I'm going to send a message to the Contrail agent saying, please tell me what to do with this flow from here on out. It programs a preemptive entry in its flow table, but it doesn't populate it with what to do, because it relies on the Contrail agent to make that decision. Now the Contrail agent will go consult its access control lists and so forth and so on, and decide, okay, this packet should pass, this packet should be natted, or it should be dropped. Let's just say in this case that traffic is going to be passed through. So it programs a final disposition for that packet in the flow table, and it sends down a message saying, okay, you're good to go with this flow. You can release any held packets. Now, at that point, our offload API kicks in, because we've hooked into that message that says, oh, okay, you can release packets and start processing that flow. And it takes note of the fact that that flow has been programmed, and it correspondingly sends a message down to the NFP saying, okay, program a new flow in the NFP's copy of this flow table. Okay. And after it has done that, the vRouter data path in the kernel will then say, okay, I'm ready to transmit the packet. Oh, this packet's supposed to go to, it's supposed to be decapsulated, and it's supposed to go to VM0, which is on virtual interface 0. So again, it doesn't have direct access to virtual interface 0, so but it thinks that it does through the virtual interface 0 representative interface. So it transmits the packet over the representative interface, which delivers it down to the vRouter data path in the NFP, which then says, oh, well, this requires direct delivery. It's already been handled by the kernel module, so I just have to send it on to where it's supposed to go. That's virtual interface 0. Let me transmit the packet up to the VM. It does so, and that ends up going via the VirtIO relay in this particular picture into VM0. Okay, so far, from what we're seeing here, it looks like all we've done is actually add a layer of complexity to the data path, and that wouldn't be very good, would it? But the real win comes next when we start transmitting and receiving packets during the rest of the flow. Because from here, when a packet arrives from the VM, or a packet arrives from the physical interface destined for that VM on the same flow, the packet will come in, and the vRouter data path will say, oh, I see this packet. I know exactly what to do with this packet. It matches this flow, and according to its routing, it's going out this interface, or it's going out, it's going out this interface, whether that's the underlay onto the underlay network with encapsulation, or to the virtual machine. And so basically, all the rest of the traffic that's going through the system completely bypasses the vRouter kernel module. and we basically have handled it in the NFP. So now all this time, of course, we're keeping statistics about what is going on, so that if the vRouter kernel module or even the Contrail agent is trying to query and say, okay, by the way, what's going on with this, they'll get accurate information about how this flow is being processed. But otherwise, they just don't even realize that all of this traffic is going through the system and they're not involved. Okay. So next I want to talk about how this then breaks out in software. And in order to do this, I'm going to mainly just talk you through some diagrams of the architecture. They're followed by slides that rehash the points that I'm discussing verbally. So I'm going to skip over the subsequent slides or just show them briefly. But that's more for people who are looking at this presentation after the fact. But mostly I'm going to talk to the diagrams themselves. Okay, so we'll start with our NFP vRouter.ko kernel module that hooks into the vRouter.ko. So this is just sort of zooming in a little bit to that picture, and you can see that this module interfaces with the vRouter kernel module primarily through the representative interfaces and those callbacks, as mentioned. So whenever we get an offload callback from the vRouter kernel module itself, we can handle it in possibly 3 ways. Okay, and those are somewhat interesting. One of the 3 ways is just if it's a very simple non-performant configuration, say, okay, add a new interface or take this interface down, then we can directly make those modifications by reading and writing across PCIe into the NIC and programming the tables and configurations that way. And that's this middle path, this middle black set of arrows that say config updates and state read. Okay, but certain operations like flow updates are fairly high rate of speed, and doing that via direct PCIe reads and writes would actually be rather slow. So for those kind of operations, instead we actually convert the request into a packet, a special encapsulated packet that we deliver across our across PCIe and our packetized and basically a special NIC that is reserved, a special virtual NIC that is reserved for this purpose. And so every sort of flow update then gets propagated down to the NFP at packet rates rather than at PCIe read and write rates. And that's this red flow updates arrow that we see here. Then we have another class of operations which are all pertaining to the update of the routing table. Now, the routing table is an interesting use case for the NFP, because the NFP has some fantastic lookup capabilities for things like longest prefix matching. It can do well, I believe the high-end versions can do, well, basically each lookup engine can do about 150 million longest prefix matched lookups, and there are 6 of them in some of these NFPs. So you can do enormous amounts of lookups, and far more than we need. But they require building of a specialized data structure in the NFP memory, and that takes a little bit of time. And as route updates come in, we don't want to be blocking other operations in the vRouter kernel module while we take the time to build rebuild those routing tables. So we have a separate kernel thread, that's this fib manager thread off to the left, that as we receive route updates, it batches them together and then basically builds a new routing table with those updates. And our routing table is basically double buffered in the NFP, so it builds a new routing table, and then when it's finished doing that over regular PCIe reads and writes, it sends one more reader write to signal the NFP, one more write to signal the NFP that it needs to go and change to switch over to using the new version of the routing table. So again, 3 different ways of interfacing with the NFP over the PCIe. And then sort of last but not least, we also have the packets, those fallback packets that I mentioned, the ones that we're not handling in the NFP. They come in through PCIe and they get delivered over a common VNIC but encapsulated to the representative interface subsystem, which then demultiplexes them to the virtual NetDevs and delivers them to the vRouter kernel module, or vice versa. As the vRouter kernel module delivers packets to the representative interfaces, we encapsulate them and mux them and send them down over the control channel. And as I said, those are all the points. This slide is just all the points that I just discussed. So now let's move down to the NFP side of the software. So in the NFP side of the software, we architected our software in a way that we hope to maximize the CPU usage for the most common case, which is the packet processing. And for that purpose, what we do is that we create a large pool of our flow processors or microengines, that's the MEs, that all in parallel are receiving packets both from PCIe and from our network block interface, NBI, which is our interface to the physical ports in the system. So that's what the worker MEs in the center of this picture represent, and they're the bulk of the microengines in the system. 48 of the 72. And each one of these 48 MEs has 8 hardware threads that, for those of you not familiar with the architecture of the NFP, are each able to post memory up to 15 memory transactions simultaneously, and each one supporting 8 hardware threads that I think I said that already, I'm sorry, but that can be switched with the 0 cycle overhead going from one thread to the other. So it gives us an incredible amount of ability to process things in parallel. But fortunately, the software for this, actually the software model for this is much simpler than one might have to worry about in such a massively parallel environment, because each one of these threads basically just follows a run to completion model. Each one reads the next packet that they can get and processes it from beginning to end to its completion, with some small exceptions for mirroring, and then delivers it to its final destination. And then it goes and gets the next packet and does the same. Now you could imagine with a large pool of threads, so we're at what, 48 times 8, 192, is that right? 100, yeah, anyways. No, 300 and more than that. I'm sorry, I'm not going to do the math in my head. Anyways, with the 48 times 8 threads that are all processing packets, you can imagine that the packets themselves can get a little bit or a lot out of order from each other, and that is not desirable in real networks, right? And so the way we handle this is, as packets arrive from PCIe or from the NBI block, we assign them each a sequence number that denotes their arrival order. And then before transmission, we hand them off to a high-speed reorder block subsystem, which puts them back into their original arrival order before delivery to their final destination. So that's what that reorder block to the right looks like. In order to make these MEs operate as fast as possible, we want to basically, again, another pitfall of parallelism is locking and lock contention. So we basically made these workers completely lockless. They all have read-only access to almost all the data structures except for statistics, which are obviously write access, in the system. And so, for example, when the worker ME wants to go and do a route lookup or do a flow lookup, they are able to always look at a there is no locking required, not even a read lock required, in order to read the entries of in the flow table or the route table or the interface table. This is because the NFP has the ability to atomically update up to 128 bytes at a time in any of its memories. And so you can replace a flow table entry wholesale or a route and or switch the double buffering on the route table instantly, and know that you have a consistent view of the system at any point in time. And then we leave the updates for those tables in separate MEs, like, for example, the management MEs, like this flow management ME that's off on the left-hand side of this picture. Okay. The statistics updates in this are also making use of the NFP's very rich atomic operations that can do that. We can actually issue an instruction with the ME that says, here, update these 5 statistics for me atomically, and the memory controller will do the appropriate behind the scenes without the workers even having to think about it, lock the cache line, modify the statistics, and write it back to DRAM when necessary. And it can do those at an incredibly high rate of speed, like 500 million operations per second for each atomic engine, and there are many of them in the system, like 20, 30. So there's no, again, these worker MEs can be kept simple, they can be kept light, they can be kept lockless, and that enables them to move at some serious speed. We also added some the other subsystems that you might see around here, that we added and pulled out the logic for performing mirroring in the system. Contrail has a very rich mirroring API, which allows it to mirror, say, every packet that comes in and out of a particular interface, but it also allows you to policy-based mirror and say, based on some sort of a wildcard classification, I want to mirror this type of traffic. And that disposition gets stored in the flow table for each new flow, but the mirroring itself then follows various rules about special encapsulation, user added data, and so forth. And so again, to keep the ME workers light, we actually made that a sort of a look-aside coprocessor within the NFP by assigning a bunch of special purpose MEs for that function. Okay. So what are the results of all of this? What have we learned, and what have we learned? First of all, we were able to successfully offload this system. We were able to demonstrate in a test that was provided to us by a customer who wanted this as real-world test that they dictated, including incorporation of external components in the system beyond just our component. 20 million packets per second, no drop performance with an IMIX distribution of traffic going through VNFs, and instead of taking 8 to 10, 12 cores in order to deliver this, which is what it normally would have taken on this compute node, we were able to do it with 1 core dedicated to the system, because in this case we were using SRIOV, and it was idle most of the time because it was actually only dealing with flow classification. We've done other tests where we can sustain over 27 million packets per second using DPDK packet gen tests, and so we know this data plane can go even faster, but those are a bit canned insofar as now we're not paying attention to real network stacks and so forth and so on. All of these performance results are always a terrible thing to talk about. I'm very proud. We're very proud of of this data plane. But everybody will always question, well, did it really do this? Did it really do that? And what tests did you do it under? And we don't have time to go into that here. However, our colleagues will be discussing the test methodology and how we got these results in very good detail in 2 weeks' time. So I encourage you to join that webinar if you don't believe me, and you shouldn't, without some questioning. But to find out more about how we measured this. Okay.
One thing I'd like to add is
Yeah.
all packet per second tests like that most people do, in particular in this case with Contrail, are done after the flows have been set up. So the flow setups have been done, and then traffic is sent on those flow entries and then measured. So flow setup is not part of any of these tests, just for truth in advertising.
Now, we have done separate flow setup tests, and in this case, it would be accurate to say that it would be absolutely accurate to say that the NFP is not the bottleneck in any of the flow setup tests. At this point, the flow setup rate is what it is, but it's as good as the Contrail system is currently able to support. And so that'll probably also be talked about in a couple weeks. So. Yep. Okay. So what are some conclusions that we drew from this exercise? We set out to have a performant offload, and we wanted it to be transparent. Well, we've talked about the performance, but just about the transparency, a couple of interesting points. First of all, we're able to do a transparent offload in the first place because of the programmable nature of the NFP. Right, the fact that we can adapt it to different types of workloads, whatever we could imagine, in this case a particular data plane, means that we can that we only have to copy the configuration, basically copy the algorithms that are used in the data plane down into the NFP, and mirror any state updates that occur in the main data plane down to the NFP as needed. And as we showed by upstreaming this into the greater OpenContrail code base within the community, this can be made entirely hardware neutral. So if anybody else comes along with a SmartNIC, they can take advantage of the same sort of facilities and do something similar. But it's that programmability that enables it to be is key to being transparent, because that way you don't have to change the data plane in any significant way in order to accommodate the hardware. Similarly, well, not similarly, but another important aspect of this is that if you go for transparent offload, you don't make the data plane aware of the hardware in any significant way, then it's feasible to offload to a SmartNIC, even if you're not offloading 100% of the functionality. You can pick and choose, which components of that you're going to accelerate and which components you're not, and you just let that traffic fall back to the original data plane for its handling. And in practice, sophisticated data planes like OVS or vRouter, and I'm sure there are others we can bring up, OVSTC. They've kind of followed the 90-10 rule, right, where 90% of the work is done by 10% of the code. And so that very much lends itself to, okay, pick the important 10%, put it on a SmartNIC as your first stab at offload, and then let the rest fall back to the main data plane. Okay. So what are we going to do in the future? Well, this was a very interesting project and great exercise. But we've got more to do, because the great thing about a software-defined network is that it can evolve at the speed of software. So Contrail is continuing to evolve, and as it does, we're going to move with it. So we're going to add support for the Contrail 4.0 feature set. We're going to add quality of service offloads in the SmartNIC, which wasn't part of Contrail when we started the project, but has been added now. We're going to add support for multi-card servers. We're going to add better support for container-based deployments. And we're going to look at other. Right now, we're mainly working with, KVM-type deployments, but we're going to look at other hypervisors as well, VMware in particular. Red Hat, yep. We're going to add support for another thing you can do in this kind of an architecture is not only can you offload the main data plane in the hypervisor, but you could offload the virtual data planes that are in VNFs. And so we're going to look at how one can do that in a fair and consistent way, so that when people might be so that people might be able to move some of the VNF processing now down into the NIC and not have to have necessarily all the traffic going in through the VMs if it's not needed. And ultimately, you know, as you can see, there's that flow classification takes a rather long path up through the host. And that's, again, part of the Contrail architecture at the moment. But we're looking at ways that we can start offloading that classification with the Contrail community's, you know, blessing and help here into the NFP itself to accelerate that as well and be able to handle that. So that's the end of our presentation, and we've had some questions come in. So let's start taking them in, and if you have more, please send them on while we're answering these.
So I can start, and we'll start from questions that are like have a shorter answer to questions that can be another dissertation.
Yeah.
And I'll answer, and Chris is free to disagree, agree, or confirm what I'm saying, or extend what I'm saying. So so what kind of flows does vRouter support? So we do support it. Well, I mean, Contrail itself supports v4, v6. It's your basic 5-tuple with like an interface or a ingress context that it handles. And I think if you're sending non-IP v4, v6 traffic, so TCP UDP will be the 5-tuple. Anything else is probably like a 3-tuple, again with the ingress context. And if you're sending non-IP v6, I think it's either slow path or it's you do it as an L2 overlay. You tend to create an L2 overlay if you have non-IP ether types that you care about.
Yeah, so we can still route and switch those, but the Contrail system itself just has no concept of policy for matching, you know, how matching ACLs or whatnot, other than, you know, the very coarse Ethernet level, and those of course still get, you know, applied, applied and forwarded. And so traffic will still flow, and it can even be accelerated in the case of an L2 network. It's not managed by Contrail's policies, right?
So another question, is PCIe bandwidth a factor in the acceleration? And Chris will give you numbers in his head. But I'll state that in the testing that we've been doing, it's not, and we've been typically limited by trying to get the host or maybe some other bottleneck. I think we can do higher than the 20. So the 20 million packet per second number in that case was 2 VMs, and I think the 27 number that Chris had on there was basically user space packet gen. Yeah. But I don't think we're hitting any PCIe bandwidth issues in the 20 million packets per second. I think we're hitting some either host limitation or we just can't get, in most cases, the VNFs aren't keeping up with we can deliver more packets to the host primarily than what some VNFs can actually handle. So anything you want to add, Chris?
Just that it is possible for the PCIe bandwidth to become a factor in some cases against certain VM to VM traffic. You'll see it more. I mean, VM to underlay and underlay to VM, it's, you know, we're at the same bandwidth as a NIC. But, you know, when you do VM to VM now, you have to factor in PCIe bandwidth as compared, for moving from one VM to another. It can be, but I'm trying to think if I think when we measured it so far, it hasn't been, well, put it this way, it hasn't been a limiting factor for anybody that's actually been testing it so far. That's what I can say for sure. You want to take the short flow question?
Yeah, okay. So what is the performance with short flows? And so how does the system behave under short flows? How do I answer this question? So we kind of alluded to the answers throughout the talk. And that's why I added the caveat that with the PPS numbers, we typically do the flow setup. So if you prime the flows, the PPS numbers won't change from what we've talked about. if you're talking about a scenario where you're, doing the testing is a whole discussion unto itself and how you craft its test setup, but that's why I primarily caveated how most people, not just us, do PPS type testing. So when you're talking, if you want to talk about how the system overall behaves with larger number of flows, as Chris said, you get the best benefit if you're able to cut through the flows. The NFP is not the bottleneck in terms of handling a large number of flows or a large connection number. What you're getting into now is you're getting into how fast can the agent apply policy or apply the security group in the OpenStack parlance to those flows, and then so you're going through the Contrail vRouter, then you're going to the agent for a classification decision for that flow. So you're really in a connection setup case. You're talking about how fast can those modules operate. And there's ways to, and if you don't need security groups being applied, you can actually eliminate the agent part of that path and speed things up. So I don't have a specific answer to give. I'm not going to quote numbers that I can't back up, but those are the things that influence if your question is more toward if you have a high connection rate but if you're packet blasting. So again, the other caveat I want to add with the PPS numbers are, at least with the 21, is it was a no drop type scenario.
200 byte average packet size, right. But IMIX distribution.
Right. Yeah. 27 number was packet gen, so that's a packet blasting scenario. I think in all cases, if you're packet blasting and you're not so much concerned about a no drop test, you're going to get a significant throughput through, regardless of whether you've got a lot of connections coming in as they come in. But the connection setup will be limited by the host.
All right.
So moving on to other questions.
Let's talk about the how do we replicate statistics question quickly. The answer is we actually take two different approaches, and it depends on the statistics. For statistics like interface statistics that don't get queried very often, and I mean often, like only when somebody wants to go and say how many packets were received on the interface, right? Those sorts of things, happen in order seconds, minutes, right? For those, what will happen is the statistic request will come into the vRouter kernel module, and we will proxy that, and we will catch that in an offload hook, and we will then read from PCIe the statistics that we've been keeping on those and add them in. Now, there are other statistics, like in the Linux netdevs. Those don't have, sort of an offload API. For those sorts of statistics, we actually have we actually are proactively pushing up via that control channel updates to those statistics on the host, and then our kernel module is adding those into the netdev statistics.
And then there's the per flow
statistics. And then the per flow statistics. Now the per flow statistics, that's a very good point, Typhoon. Those have to be updated much more, frequently, and that table is rather big. It's millions of flows, right? And so you don't want to just copy the entire table up all the time. So for those, what we do is we accumulate and batch groups of those statistics into packets, and we send them up as control messages over the control channel at packet rates, and then the host is able to extract those. And I say at packet rates, but it's really we're only sending thousands per second, so it's not making a significant dent in our performance.
And that's a key update, because that will be what the agent relies as far as expiry logic. So.
That's right. All right. Well, I think those are all the questions that we can handle, and we thank you very much
with the time allotted.
With the time allotted, and I thank you very much for joining us for this webinar, and we hope you have found it interesting and informative. And if you have further questions or interest, please get in contact with us, and we will be happy to talk further with you. So thank you very much.
Thank you, Ted, Chris, and Typhoon. This webinar, as well as our previous webinars, can all be found on the classroom page of the OpenNFP.org website. Thank you, everyone, for attending.